And good evening, AP Physics students. Mr. Curson coming at you here with a little example problem on electrostatics. Well, let's get charged up, folks, and let's dive right into this problem. So, this is number 13, and it says, I have 3 point charges, and Q1, Q2, Q3, and the 3 point charges are all equal in magnitude, 11.0 microcoulombs, and they're all positive. And there's a little drawing in the book, and it says all of the point charges are located 15 centimeters from each other at the corners of an equilateral triangle. So I've kind of drawn out the picture here as it shows in the book. For some reason, red positive charges are always red and negative charges are always blue. Not sure why. Just seems to be that way. And it wants to know, so then the problem says, what is the net force acting on all of these charges? All right. Well, let's get to work here. Let's get down to it. So let's start with a force diagram here. All right, so this is charge 1. What is charge 1 doing? Well, charge 1 would be exerting a force on charge 2. So I'm going to call this the force on charge 2 due to charge 1, right? And it would be repelling, going that way. What else would Q1 be doing? Well, it would be repelling Q2. So I'm going to call this Q3, F sub 3, 1. So that's the force on charge 3 due to 1. Likewise, charge 3 would be repelling charge 1. So I'm going to call this F sub, let's see, this is the force on 1 due to 3. Okay, and this guy would be being pushed this way. This is the force on 1 due to 2. And I think you probably see the pattern here. Force on 3 due to 2. And the force on 2 due to 3. All right, so those would be the forces. Now, as you know, the electrostatic force is just like any other force in that they add like vectors. So we're going to have to figure out what each of these vectors are individually, both magnitude and direction, and then we are going to have to do some vector addition in order to find out the net force acting on each charge. So let's go ahead and get to it. Let's find out what one of these forces is. What's the force on 1 due to charge 2? Well, we can use Coulomb's law to find that. That would be K Q1 Q2 divided by R squared. This K here, of course, Coulomb's law constant, not to be confused with our spring constant, which would be in newtons per meter. So we know all of these things, so let's go ahead and plug in some numbers here. K is 9.0 times 10 to the 9th. Q1 and Q2 are both 11 microcoulombs. Remember that the Greek letter mu means micro, or 10 to the minus 6th, or 1/1,000,000th of a coulomb. And I'm just going to square that because Q1 and Q2 are equal to each other. Right? And then the distance between them would be 15 centimeters. Of course, your gut reaction in any physics formula is to convert things to kilograms, meters, and seconds. So if we punch this all into our friendly calculator, I get that the magnitude of the repulsive force on charge 1 due to charge 2 is equal to about 48.4 newtons. All right. And actually, in magnitude, that's what all of these forces would be, right? Because for each of these, the charges are equal and the distances are equal. But we're not quite done yet because we still need to find the net force acting on each charge. So I'm going to just go up here and do a little zoom in here on Q1. So let's just kind of draw. Here's Q1. Ooh, that's a different color red. All right, that's all right. That'll make things interesting. All right, here's F sub 1, 2. Here is F sub 1, 3. And of course, we would know that this would be 60 degrees in here because this is an equilateral triangle, right? So this would be 60 degrees. So to find the net force acting on charge 1 would be the vector sum of these two forces. So F12 plus F13. And what would that be? Well, let's do a little head to tail vector addition here. So F's right, put F12 and then F13, and then this guy here would be the net force acting on charge 1. Now by symmetry here, if this is 60 degrees, I think it would be safe to assume that is 30 degrees. This also would be 30 degrees, and then that would make that angle in there 120 degrees. Well, I think by symmetry here, we could say, let's go ahead and define our coordinate system like this. X and Y kind of makes sense. I think we could see here that the net force on charge 1 in the x direction is 0. F12's component in the x direction would be positive. F13's component in the x direction would be negative. And by symmetry, those would cancel out. The net force on charge 1 in the y direction is non-zero though, and that would be equal to f sub 1, 2 cosine 30 degrees plus f sub 1, 3 cosine 30 degrees. In other words, I'm taking the y component of f sub 1, 2 here and adding to it the y component of f sub 1, 3. And that should get us the net force acting on charge 1. So it's the net force in the y direction, but it's also just the net force since the net force in the x direction 0. So this would be, if I plug this in, it would be 48.4 cosine 30 times 2. And I would get a net force of acting on charge 1 would 83.8 newtons. And of course it asks for the magnitude and direction of the charge. So I would have to indicate a direction here. I would say in the plus y direction. Okay. By symmetry, let's see if we could do the same. The net force acting on charge 2 here would also be 83.8 newtons, right? Because we would kind of have the same vectors we'd be adding here. But the direction here would be halfway between these two guys, right? So I would call that at an angle of 30 degrees below the minus x axis. Right? We've defined this to be our plus x direction, so this would be the minus x direction, and it would be 30 degrees below. And then the net force on 3 would also be 83.8 newtons, but this time at an angle of 30 degrees below the plus x axis. How did I come up with that? Well, again, by symmetry, our net force here would be the same. And this is 0 degrees, that's negative 60 degrees. These are nice and equal. So we would have, this would be the net force on 3, 2, 2, 1, and 2. All right, physicists, nice work for your joke today. I have some props, and the joke goes like this. Duct tape. Ha ha. Is there anything it can't do? Here's my joke today. Duct tape. How is duct tape like the Force? We've been speaking about forces, but I mean the Force from Star Wars. How is duct tape like the Force? Well, both duct tape and the Force have a light side and a dark side and bind the universe together. Jokes that involve Star Wars, duct tapes, physics. Oh, what great things. All right, nice job, physicists. We'll see you tomorrow.